Folks. Today we're going to learn about properties of exponents. And exponents are hopefully something you're familiar with from middle school math. But in case you need a bit of a refresher, let's go over some vocab to do with exponents. So when we have uh, something like this here, this is called a power when we have a base raised to an exponent. And it's a representation that shows how many times to multiply a quantity. And so if we have something like 5 to the third power, 5 cubed, that means 5 times 5 times 5. So we've taken this base number, 5, and the base number is the quantity that we multiply by itself. And we raise it to an exponent, in this case, the 3, and that's the number of times that you multiply the quantity. So it's why we've got 3 5s here that are multiplied together, because this was 5 to the third power. And so this total is 125. 5 times 5 times 5 is 125. Another thing that's going to be important as we're going along is understanding what a reciprocal is. And a reciprocal is just flipping a fraction. A number times its reciprocal should equal 1. So if we have the fraction 1/8 and we flip that fraction, that's 8. You can think of it as 8 over 1, but of course 8 over 1 is the same as 8. And then if we were to multiply those two fractions together, we would get 8 over 8, which is the same as 1. So reciprocal is just flipping a fraction. So keep those vocabulary words in mind as we're going through these examples. Hi, folks. Today we're going to be learning about properties of exponents. And exponents are part of powers, which are representations that show how many times to multiply a quantity. So here I've got an example of a power, 10 to the ninth power. 10 is the base and 9 is the exponent. So the base is written in the large font and the exponent is written in small font up in the top right corner. So just to be clear, the base is the quantity that is multiplied by itself in a power expression. And so here we've got 5 to the third power. And so 5 is the quantity that we multiply by itself over and over again. How do we know how many times to multiply 5 by itself? Because we look at the exponent. And the exponent, in this case 3, tells us how many times to multiply a quantity by itself. Which is why we multiplied 5 by itself 3 times here. 5 times 5 times 5 is 125. Another word that you're going to need to know as we're going through these definitions or these examples is what a reciprocal is. And a reciprocal is just flipping a fraction. So if I have the fraction 1 over 8 and I flip that fraction, I get 8 over 1, which is, of course, the same as 8. These two fractions are reciprocals of each other. And we can tell that they're reciprocals of each other because if we multiply the reciprocals times each other, we get it equals 1. So 1 over 8 times 8 over 1 gives us 8 over 8, and that's the same as 1. And you can do this with negative numbers. So negative 4/5. If we flip that fraction, that would be the same as negative 5/4. And again, if we multiply those two together, we would get positive 20 over 20. So keep those definitions in mind as we're going through these problems in case you're unclear about what any of the vocabulary words mean. So let's start off looking at how to handle zero exponents. For each of these examples, I've kind of written the definition 3 ways. I've written it in words, I've written it in numbers, and I've written it as an algebraic expression. So pay attention as we go along to which one of the definitions makes most sense to you. You don't have to write down all 3 of them. Write down the 1 or 2 definitions that make most sense to you. So the rule here for zero exponents is that so long as a is not 0, anything raised to the 0 power equals 1. If you've got 0 to the 0 power, that's undefined. If you try to punch it into your calculator, you'll get an error message. So it doesn't matter what I raise to the 0 power. 6.7 to the 0 power, that equals 1. -9 to the 0 power, that equals 1. Now, I'd like for you to pause for a moment and use the calculator that you're going to use on a test. And I want you to actually try to plug -9 to the 0 power in your calculator. There's a reason I wrote it here in parentheses. Your calculator is very strict about doing order of operations. If you just type -9 to the 0 power, you will get -1 as your answer because your calculator does exponents before it does multiplication. So it does 9 to the 0 power and then it multiplies by -1. So if you're trying to raise -9 to the 0 power, you need to put that -9 in parentheses. So keep that in mind when you're doing these problems if you're trying to raise a negative number to an exponent. Let's look at negative exponents now. If you have a negative exponent, so long as a is not 0, a to the negative n is the reciprocal of a to the positive n. To do an example, in numbers, 4 to the -2 power is the same as 1 over 4 squared. So I took the reciprocal of 4, which is 1/4, and then I have squared that 4 value. It's a positive 2 exponent now instead of a negative 2 exponent. So let's look at how this looks here with an example. I've got -2 to the -4 power. So that's going to be the same as 1 over -2 to the +4 power. And now -2, notice I didn't lose the negative sign in front of the 2. The only negative sign I lost is on the exponent. So 1 over -2 to the 4th power is the same as 1 over 16. -2 to the 4th power is +16. And so I have evaluated this power expression and I got the answer 1/16. Let's look at an example that uses variables instead of numbers. So here we have 4 times x to the 0 power divided by y to the -3rd. So once again, we have one of these negative exponents here. Um, and we're asked to simplify and write the answer using only positive exponents. We need to get rid of that -3 there. What I'm going to do first is because I have x to the 0 power, I know x to the 0 power is just 1. So I'm going to rewrite this as being 4 times 1 divided by y to the -3. And now, just to make it a little clearer what I'm doing, y is raised to a -3 power. 4 is not raised to a negative power, so I don't want to try to flip a fraction that has 4 in it. I don't want 4 to be in this fraction that I'm flipping. So I'm going to separate out, I'm going to write this as a multiplication problem, 4 times 1 over y to the -3. And that'll make it a little clearer about why I'm flipping the fraction that has y in it and not the one that has 4 in it. So because y has a negative exponent here, I need to, well, first of all, 4 doesn't have a negative exponent. So 4 is still 4. I didn't flip that fraction. But now instead of having 1 over y to the -3, I'm going to have y to the +3 over 1. Remember, when you flip the fraction, you change the sign on the exponent. And now y to the 3rd divided by 1 is just y to the 3rd. So I can simplify this a little bit further. My final answer is 4y cubed. So have a look at it. I know students often find problems written with variables trickier than problems written with numbers. So pause the video if you need to and take a little bit more time looking at each step and where each number comes from. Let's move on to product of powers. With this property, you'll see that so long as our two powers have the same base, in this case, the base is 3, then all we need to do is add the exponents together to get our answer. So instead of having two separate powers multiplied together, I'm going to write this as a single power, 3 to the 2 plus 6 And of course, 2 plus 6 is 8. So I can simplify this as 3 to the 8th power. Notice here I'm asked to simplify, whereas up here I was asked to evaluate. Here I wanted to get a final numeric answer, and here I'm leaving it in a power format. It's asking me to express my answer with an exponent. Similarly, for part D, when we do the quotient of powers, again, we want our answer to be left in exponent in power form. So let's look at what we do with quotients. When we divide powers again, with the same base, then we subtract those exponents. So if we have negative 4 squared divided by negative 4 to the 7th power, that's the same as negative 4 to the 2 minus 7 power. And of course, 2 minus 7 is negative 5. Although what I've written here is mathematically correct, I haven't finished the problem because writing things with negative exponents is generally considered incomplete. We were asked to write our simplification with positive exponents. So what I need to do is I need to think about my negative exponents rule that we did up above, and I need to flip the fraction for the value being raised to a negative exponent. So I'll rewrite this as 1 over negative 4 to the positive 5th power. The 4 still has a negative in front of it, but I'm raising it to the positive 5th power. Because I'm simplifying, not evaluating, I am finished at this point. I've written my expressions with only positive exponents. Let's look at doing the power of a power. We're supposed to simplify this expression when we've got z to the 4th power, and then that quantity is raised to the negative 3rd power. When we have the power of the power, we multiply the exponents together. So here I've got 4 and negative 3, so I'm going to rewrite this as z to the 4 times negative 3. And 4 times negative 3 is 12, so that's going to be z to the negative 12 power. Here, what I've written is mathematically correct, but I haven't finished because I'm supposed to give my answer using only positive exponents. So just as we did with the last example, we are going to flip the fraction, 1 over z, and now instead of having the exponent be negative 12, the exponent becomes positive 12. So 1 over z to the 12th power is the final answer here. Power of a product. If you kind of multiply two numbers, have a quantity where you're multiplying two numbers together, and then you raise it to a power, then what you do is you take that exponent and you apply it to each value being multiplied in the multiplication problem. Now, if we were just strictly given numbers, you would say, of course, that's, or you would probably say, well, just do 3 times 2 is 6 and raise that to the 5th power. That works with number values, but quite often we're given examples like what you see here in problem F, where there's a number multiplied with a variable. And of course, we don't know what the variable is worth, so we don't know what value we get from multiplying those two together. So we can't just use the, PEMDAS order, do what's in parentheses first. So this is a very important rule to know. So what we do here is we apply this exponent of 2 to the negative 1.5, and we apply it to the y squared, still multiplying the numbers together. So this is going to equal negative 1.5 squared times y squared. So we're taking that 2 exponent and applying it to both the negative 1.5 and the y. Now, we're supposed to just simplify this, not evaluate it, but it's not possible to evaluate it when we have a variable there anyway. So I'm going to simplify this part a little bit further. Negative 1.5 times negative 1.5 is positive 2.25. and we're still multiplying by y squared. So 2.25y squared is my final answer here. Simplifying these expressions when we're using the power of a quotient property. Very similar to product of a power, a power of a product property. Again, we're taking this exponent and we're applying it to each value in the division problem. So, if I take a divided by -10 and raise it to the third power, that's the same as a to the third power divided by -10 to the third power. I can simplify that -10 to the third power a little bit more. That's the same as -1000. So I have a cubed, or a to the third power, divided by -1000. Let's look at another example. 3d divided by 2 to the fourth power. If it's helpful to you, you can break this down into two steps. So I've got whatever's in the numerator raised to the fourth power and whatever in the denominator raised to the fourth power. But then you can see that this multiplication problem kind of goes back up to what we looked at in part F, where that 4 is going to apply to the 4 exponent is going to apply to the 3 as well as the d. So I can kind of further apply that 4 exponent to the 3 as well as the d. Now, in this example, I'm asked to simplify, so I can simplify a little further. 3 to the fourth power is 81. D to the fourth power just stays as is, and 2 to the fourth power is 16. And so this is my final answer here. One more example. Let's practice something with one of those negative exponents again. So if I have 2x divided by 3, the whole quantity raised to the -5th power, then that whole fraction can be flipped because the whole thing was raised to the -5th power. So I can rewrite this as 3 divided by 2x raised to the +5th power. Now, this problem is very similar to the second example we just did above. We are going to take that 5 and apply it to each component of the division problem. We've got 3 to the 5th divided by 2 to the 5th times x to the 5th. Each of those components of the multiplication or division problem have that exponent of 5 attached to them. So we're going to, let's see, 3 to the 5th power is 243. 2 to the 5th power is 32, and I've got x to the 5th. So this is kind of the final answer here when I simplify that expression. So let's look at some real world examples why these kind of manipulations would be useful. For instance, in this example here, we have a can of food, and I want to know the volume of this can of food. How much space is there inside the can? And so the volume of a can, of a cylinder, is calculated using the equation V equals pi r squared times h. Really, many 3D objects are just calculated as doing the area of the base times the height, and that's all we're doing here. It's the area of the circle, the lid of the can, times the height of the can. But I'm given a little bit more information here. The height of the can is given as h, but the radius is going to be h divided by 2. So the radius is given in terms of the height, rather than having them be two totally separate variables. There actually is a relationship between the radius and the height. So if I write out this equation, V equals pi r squared times h, and then I want to plug this value in for my radius. So that's pi times h divided by 2 squared times h. And we want to simplify this so that it's in simplest terms for this particular can. And so here you can see we've got a fraction, we've got a division problem, and we're squaring that fraction. So this is very similar to part G above, and we're going to use that same strategy where we apply the exponent 2 to every component of the division problem. So I'm going to have pi times h squared divided by 2 squared times h. Well, now here I have kind of the situation that we had back in part C, the a product of powers property, where I have h squared times h to just the first power. It's not written there, but the implication is that this is just the first power when no exponent is written. And so I can now do this as h to the 2 plus 1. So that's pi times h to the 2 plus 1 divided by 2 squared, which is pi times h cubed divided by 4. I'm just evaluating the 2 squared is just the same as 4. And then this is our final answer. And this would probably more typically be written pi divided by 4 h cubed. Because pi is a number value, 3.14159 goes on forever. We would write the pi over 4 together and the variable, the h value, by itself. But those two expressions mean the same thing. So that's a real world example of why you might want to kind of rearrange exponents to help you simplify an expression or an equation. Lastly, this is going to become super important in science classes, but scientific notation uses powers, uses exponents to write number values. It's especially useful when you have very large or very small numbers. So for instance, a jellyfish emits about 1.25 times 10 to the 8th photons. That's a whole lot of photons. In not very much time, 6.25 times 10 to the negative 4th seconds, that's a quite short period of time. When you've got positive exponents, that represents really large numbers. When you have negative exponents, that represents really small numbers. Here we're being asked to calculate the number of photons per second. So we want to do photons, 1.25 times 10 to the 8th photons per second. So I want to divide by 6.25 times 10 to the negative 4th seconds. And that gives us, you can see from the math problem, photons per second. Photons divided by second. It's going to give us a rate. I'm going to just undo that circle though, because you can't see my exponents very clearly. Let's focus on the math problem now. I'm going to kind of separate this into two separate fractions. I'm going to have this fraction where I'm dividing the coefficients, and then this fraction where I'm dividing the powers. In scientific notation, the number out front is called the coefficient, and then you have the power of 10. The exponent is, of course, that small number value attached to the 10. The coefficient has to be a number between 1 and 10. So if that's not something you remember, you might want to add it into your notes. Coefficient for correct scientific notation must be greater than or equal to 1, but less than 10. Okay. So if I've got 1.25 divided by 6.25, that's going to equal 0.2. And, oops, I didn't mean to put an equal sign there. And we're going to focus on those exponents next. We've got a division problem here. And when we divide exponents, we're going to have that, we're going to do it as a subtraction problem. We're going to subtract those exponents. So we've got 8 minus negative 4. And so I had 0.2 as my coefficient, but my exponent here is going to be 10 to the 12th because 8 minus -4 equals 12. Now, I have an answer here, and it seems to be in scientific notation, but it's not actually correct scientific notation because my coefficient must be a value between 1 and 10. And here my coefficient is less than 1. So this is not correct scientific notation. To make it correct scientific notation, I need to move the decimal point to get a number between 1 and 10. So I move the decimal point one time. Okay. But of course, if you move the decimal point, you change the value of the number. We don't want to do that. We want to have an equal statement here. If you look, I took this number from 0.20 to 2. That, I made the number bigger by moving the decimal point one time. Because I made this number bigger, I have to make this number smaller to compensate. And I'm going to make it smaller by just a value of 1. Why 1? Because I moved the decimal point just one time. So my final answer here will be 2.0 times 10 to the 11th power, and that is in photons per second. So that's a whole lot of photons in 1 second. That's the scientific notation form, but writing this out in standard form, just so you can refresh your memory from middle school, how this looks. This would be let's see, we're going to move the decimal point 11 times, okay? When you see an exponent, when you've got a positive exponent, that means that the standard form is big, because you're multiplying by powers of 10. If you've got a negative exponent, the standard form is small because you're dividing by powers of 10. But I'm multiplying by 10 11 times here. So I'm going to move the decimal point 11 times. So it started here, and I'm going to move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So my final answer here is 200 billion photons per second. Make sure you erase your original decimal point. If the decimal point is there, the value is 2. So we want to erase that decimal point so that the value of this number is 200 billion. I hope this helped.